In this demo video, I'm going to present FuzzTastic, a tool that allows to perform coverage-based fuzzer evaluations. Existing evaluations capture the inputs from the fuzzer queue, which is basically a directory that contains coverage-increasing input files, and then replay them on a second instance of the same program compiled with coverage support enabled. This approach has two limitations. First, it inhibits measuring the number of executions of code region which, if available, would allow to identify barely tested code. Second, due to path collisions in fuzzers that hash coverage information, not all generated fuzz inputs that increase coverage are added to the queue, resulting in distorted evaluations. To address these limitations, we developed FuzzTastic, a fuzzer-independent coverage analyzer that enables practitioners and researchers to perform uniform and reliable fuzzer evaluations. FuzzTastic's coverage analysis approach is split into two steps. In the first step, the source code of the target program is translated into LLVM's intermediate representation to extract basic block metadata, as well as to apply the instrumentation passes for tracking code coverage required by FuzzTastic and the respective fuzzer. In the second step, the actual coverage analysis is performed. Here, FuzzTastic starts the fuzzing campaign and then repeatedly persists the coverage information stored in a shared memory segment into separate coverage reports. While FuzzTastic itself is written in Python, the entire configuration to automatically perform coverage-based fuzzer evaluations is specified via bash scripts and Docker files. Here we can see the scripts to evaluate the AFL fuzzer on the target program GIF to PNG. On the left side, we see the bash functions to build GIF to PNG and to apply FuzzTastic's coverage instrumentation. This function is then called with AFL's compiler wrappers from the function AFL instrument exec to also apply the fuzz-specific instrumentation. Finally, on the right side, we can see the function to start the fuzzing campaign. Once the scripts are fully specified, we can create a Docker container for the fuzzer evaluation. For this, we provide the bash script build containers, which take the name of the target program and that of the fuzzer as input parameters. In this process, first the AFL fuzzer is built, followed by extracting the basic block metadata from GIF to PNG. After that, GIF to PNG is instrumented and compiled into a fuzzable binary. We are now inside the Docker container. Using the script monitor fuzzer, we can now start the fuzzing campaign as well as FuzzTastic to monitor the basic blocks covered. For this, we specify GIF to PNG as the target program, AFL as the fuzzer, 1 hour and seconds as the fuzzing timeout, and tool demo as the output directory for the coverage reports. Note that the directory of the seeds we already specified in one of the bash scripts we have seen before. During the fuzzing campaign, FuzzTastic generated a coverage report every 15 minutes. The report we obtained after 1 hour of fuzzing is shown on the right, while the metadata of basic blocks extracted while building GIF to PNG is shown on the left. Here we can see the ID of the basic block as well as the name of the file and the function where the block is located. In addition to that, we extract the source code line numbers enclosed by each block. The block ID thereby serves as index in the list block coverage stored in the coverage report to find out how many times a specific basic block was executed. Using our tool, we created a large-scale coverage benchmark dataset which we will release for further studies together with FuzzTastic. We also showed that path collisions in AFL-based fuzzers can cause an error of up to 9% basic blocks missed. Apart from the case study presented in our paper, FuzzTastic can also be used to perform frequency-based coverage analysis of fuzzers, to detect fuzzing roadblocks in the code, and to visualize fuzzing progress like in these animated call graphs. Here we see the fuzzing progress of the fuzzers HongFuzz and AFL executed for 24 hours on the program FreeType2. In these graphs, the green nodes indicate the function covered in all 20 trials, while the orange nodes indicate the function covered in at least one trial.